Hello everyone! I hope you guys are not tired of my online lectures. For today, or for this lecture, I am gonna discuss depth first search. Honestly, I would think this is one of the more confusing topics for many students, but let's try to make it as simple as possible for you guys. So graph traversal, there are actually two ways. We have depth first search and breadth first search, BFS or DFS. In this lesson, I will be discussing about depth first search. So in graph traversal, DFS is a systematic way of visiting vertices and arcs. So originally, when we were discussing about graphs, we didn't actually know how to traverse or to iterate through the graphs. There was no way for us to do that. We could just traverse, or we could iterate. I guess you could say we could iterate normally, wherein we start from the first index going to the last. But then that wouldn't be what's proper. There is a proper way to traverse the graph, and one of them is using DFS. This technique is called depth first search because it continues searching in a forward direction, or keeps going deeper for as long as possible. If we just take the definitions term for it, it might be a bit more confusing, but when we go through a simulation, it's a lot easier. It's also a generalization of pre-order traversals. I guess you could say it goes from top to bottom, but that's for trees. When we're talking about graphs, it doesn't necessarily have like a top or a bottom. So for example, something like this, it doesn't have a concept of going up or down. So we'll have to look at how this would work. So for DFS, this is done recursively, and this is the pseudocode on the left. So given a specific vertex of V, what does this mean? This is the vertex I am going to start my DFS from. Okay? So I'm going to start from vertex V, and then I'm declaring vertex W. This will be used later. Mark, what is mark? Mark is basically an array containing, or an array that is the same size as the number of vertices. I have 7 vertices here, which is represented by an array of 7 indices from 0 to 6. And we mark all of the elements in that specific array to be unvisited. So this specific array contains whether or not we visited a specific vertex. So initially, mark will contain unvisited, or will contain unvisited as the status. What does this mean? It means vertex 0 was not visited, vertex 1 was not visited, vertex 2 was not visited, and so on. So mark initially should be initialized with unvisited. Once it's visited, we change the value to V from U. So we're using U and V. That's only 2 values, which means it can be implemented in many ways. We could implement it using bit vector, which is rather than having U and V, we just say 0 for unvisited, 1 for visited. That can be done. We could use your favorite, which is computer word, wherein mark, rather than being an array, could be a character or something, wherein we could have from 0 to 1, and from 0 to 6, and then we set all of those unvisited indices, bits, to 0 or 1. So it's very nice. It could be anything. I hope you guys are not traumatized by computer word, because it could be we could represent mark using that. We could represent mark using any other kind of data structure. But in this case, we're representing it as an array that contains U or V, U for unvisited and V for visited. So initially, Mark will have an array containing unvisited nodes. Okay? So the start of DFS is we start by setting vertex V to be visited. So let's say we are starting at vertex 0. So I just need to set 0 to be visited. Very easy. Next, for each vertex W, that's the purpose of W, for each vertex W on LV. What is LV? L is my adjacency list representation of the graph. 0 can point to 1, 0 has an arc going to 2. 0 has an arc to 1, and 0 has an arc to 2. So that means for each vertex W on LV, what is V? V is 0. So meaning for each vertex adjacent to 0, I am going to check if mark at index W, so what are the indices we have? We have 1 and 2. Is mark at index 1 unvisited? Yes, it is. So if it is, we're gonna call DFS again. Let's go through the simulation. Now this might look very overwhelming, so just follow through with me. Okay, I don't have the animations of the great Ma'am Peña. So let's start. We started at DFS 0. My V will start at 0. So what did I do? I did mark V becomes visited. So originally, our mark all had use. We let 0 be V. Mark at index 0 set to visited. Now we're going to check for each vertex W on LV. L at index V. L at index 0, there are two vertices, 1 and 2. So we are going to check if mark W equal to invisited. So we have W1 and W2, that's 1 and 2. So we start at 1. Is 1 unvisited? 1 is unvisited. Good. So we are going to call DFS 1. So it's recursive because we're calling DFS 1. So wala pa na to gitagad si 2, okay? We're only talking about 1. So we're visiting 1. So we set 1 to visited. So mark 1 gets visited. So now that becomes V becomes, mark index 1 now becomes V. And then we're going to check all of the vertices on LV. V is 1. 1. My indices are 2 and 3. So I have W1, W2 is 2 and 3. So I'm going to start with W1. 2. Is 2 unvisited? So let's check here again. 2 is unvisited. Yes. So I'm going to call DFS again for 2. So you will notice I don't actually touch other adjacent vertices yet until I keep going down the list. It's clearer with a different example, but for this example, let's just keep going. DFS 2. V equal to 2. What are adjacent to 2? 2 is here. What are adjacent to 2? Vertex 0. So W1 equal to 0. I'm going to check, is vertex or is mark at index 0 unvisited? Mark index 0 is already visited, so I don't do anything. And because there is no other vertex left, my DFS2 or this specific function call ends, and I go back here. I'm done with vertex W1, so I'm going to go to W2, which is 3. Is 3 unvisited? 3 wasn't visited yet, so I'm gonna call DFS3, where my vertex is 3, so I'm going to set 3 to be visited, and then I'm going to check the vertices on L at index 3. L at index 3 is 0 and 2, so my vertices are 0 and 2. if mark at index W, which is W1 at this case, so is mark at index 0 visited? Yes, it is. So I'm going to go to the next vertex. Is W2 or mark at index 2 visited? Yes, it is. So I've run out of vertices to visit. So my DFS 3 ends. So I'm going here. I'm done with vertex 2 and vertex 3, or adjacent vertex 2 and 3. Are there still more vertices to visit? No more. So DFS 1 ends. So I'm going back here. I started with DFS 1 and I'm done with DFS 1. So I'm going here. W2. I'm checking 2. Is mark at index 2 already visited? Yes, it is. So my DFS ends. What you will notice is there are still 3 unvisited vertices in this specific simulation of DFS. What does that mean? If there are still unvisited vertices, we need to call DFS again. And which of these 3 vertices will we use? The answer is, it depends. So, if the example will say, maybe in the exam it will say, if DFS fails to visit all the vertices, then call the biggest unvisited vertex. So, I would call DFS 6. But if it says, call the smallest unvisited vertex, I'll call 4. Or if it says, call the middle, which is unlikely, call 5. But it doesn't matter which one you call as long as you run DFS again. So this time, we decided to call DFS 4. So we set 4 to be visited. So you'll notice 4 became visited. From here, it became visited. And then we checked for each vertex or each adjacent vertex W on LV. So we're looking at index 4. So the adjacent vertices are 5 and 6. So we have W1, W2, which is 5 and 6. I'm going to start with 5. 5 is 5 visited. 5 was not yet visited. So I'm calling DFS 5. I set V equal to 5 and I mark it as visited. So 5 became visited. What are the adjacent vertices on L at 5? List at index 5 is 1. The only adjacent vertex is 1. So W gets 1. So I'm going to check, is mark at W, has 1 been visited? Yes, it has. So my DFS ended. And I go back here. So I'm done with 5, I'll go with 6. This is my next adjacent vertex. Is 6 already visited? No, it was not yet visited. So I'm going to call DFS 6 again. V equal to 6. We are now setting mark at 6 to be visited. So it's now visited. And then we are going to check for all adjacent vertices to 6. So the adjacent vertices are 3 and 5. So W1 and W2. I'm going to check, is 3 visited? 3 is visited, so I don't do anything. Is 5 visited? 5 is already visited, so I don't do anything. But in the code, it says unvisited. So I should have just said, is index 3 unvisited? No, it's not, so I don't do anything. Is 5 unvisited? No, it's not, so I don't do anything. I end my DFS and I check mark. Is mark or are all the vertices visited? Yes, they are. So therefore, I was able to run my DFS and I have my result, which is a spanning forest. Now, you will notice something to the right side. The right side basically represents my spanning forest. So I started at index 0 and I pointed to index 1. I did DFS index 1. Once I was at index 1, I did DFS at index 2. Once my DFS 2 ended, I go back to 1 and I call DFS 3. So I point now to 3. You will notice that there are arrows coming from, or there are broken arrows coming from different vertices. What are these? So, what are these? These are basically arcs going from 0 to 2. These represent adjacent arcs. So, you will notice from 0, I have adjacency with 1 and 2. So I have I have an arc from 0 to 1 and 0 to 2. But why is it from 0 to 1 it's a black arrow, but from 0 to 2 it's a broken arrow? It just means that when I ran my DFS, I was able to encounter an adjacent index or an adjacent vertex, but it was already visited. So let's go back to our simulation. V at index 0 drew this specific vertex. I start with V at index 1. So ayaw lang sa ni sila tagda. I start at index 1. So 0 to 1, that's 1 arc. I did DFS 1, V1. From 1 to 2, is 2 already visited? No, it wasn't. So I draw an arrow to 2. And I did DFS 2. From DFS 2, I'm going to check my adjacent elements. There is a 0. Is 0 already visited? Yes, it is. So, rather than just saying, okay, don't do anything, I drew an arrow from 2 going to 0. Because 0 is already visited. And you will notice there is a color coding and it's broken lines. That's a Mampenia notation. It just means that there is a path or there is an arc going from 2 to 0. But it's already been visited, so I'm not going to draw a black arrow. I'm going to draw a different arrow that's broken going to 0. And I'm going here to 3. 3 wasn't visited yet, so from 1 I have an arrow going to 3. From 3, I have 2 vertices that are adjacent to 3. That's 0 and 2. 0 was already visited, so I have an arrow from 3 to 0, but it's a broken arrow and it's colored green. Color doesn't matter for now. We'll talk about the color later, but there's a broken arrow from 3 to 0 because when 3 tried to visit 0, it's already been visited. So the broken arrow notation is there for when a specific vertex has an arc going to an already visited vertex. 2 was already visited, so it's another broken arrow from 3 to 2. DFS ended, so I'm now here. I'm checking at 2. So 2 has already been visited and 2 has an index or adjacent to 1. So I need to draw 2 to 0. 2 to 1 ang 2 to 0 ang masabot. So you will notice that these specific broken arrows just represent when you tried to do DFS, but then the arc or the element, the vertex was already visited. That same here. 4 points to 5. 5 has an arc to 1, but 1 is already visited, so I have a broken line going to 1. 6 tries to visit 3, but 3 is already visited, so there's a broken arc from 6 to 3. Tries to visit 5, but 5 is already visited, so there's a broken arc going from 6 to 5. So we'll talk about the broken arcs now. So the result of the DFS is a depth first search spanning forest. What is a forest again? A forest is a collection of trees. So in this case, I have two different trees. So this is my spanning forest. The arcs leading to new unvisited vertices are called tree arcs. So mo ni sila ang mga black arrows. So if a vertex pointed or visited a new unvisited vertex, or if there's an arc going from a visited to an unvisited vertex, it's called a tree arc. Tree arcs form the depth-first spanning forest for the given digraph. So my depth-first search spanning forest is the ones that are in the tree arcs, or the ones that are represented in black. The other types of arcs, so it's color-coded by Ma'am Peña as well. Thank you, Ma'am Peña. Back arc is green. What does it mean? It's a non-tree arc, so it wasn't a tree arc, which goes from a vertex to one of its ancestors. So 2 points to 0, 2, the ancestor of 0, 2 is an ancestor, 2 is a descendant of 2 is a descendant of 0, and it points to 0, therefore it's a back arc. It's a descendant going to an ancestor. Forward arc is a non-tree arc which goes from a vertex to a descendant. 0 to 2. 2 is a descendant of 0, so it's a forward arc. Cross arc is a non-tree arc which goes from a vertex to another vertex that is neither an ancestor nor a descendant. These are cross arcs because 5 does not have any ascendant or descendant relationship with 1. 6 does not have a relationship with 5. They are siblings technically, but 6 and 5, they aren't as ancestors nor descendants. Same with 6 and 3, and 3 and 2. So this is our first exercise. So given this specific digraph, we need to simulate DFS. And I'm going to simulate DFS without drawing it first para sayo na siya sabton. So the concept of DFS without having to go through all of this coding jargon or this pseudocode is very simple using the mata-mata method. So let's do the mata-mata method. We will start at DFS 4, okay? So we're going to start at 4. Is 4 already visited? No, it hasn't been visited, so I'll start at 4. I have two adjacent nodes, and let's just say it's arranged in descending order, so we'll focus, ascending order, so we'll focus on the smaller value first. 4 will visit 5. So I technically did DFS 4, then I did DFS 5. So I'm at 5. I'm going to look if I have adjacent nodes. 5 points to 1. There is no other adjacent nodes for 5, so I'll go to 1. 1 has 2 adjacent nodes, 2 and 3. I go to the smaller node, that's 2. 2 has how many adjacent nodes? Only 0. So I'll go to 0. And I will only go to the next vertex if it's not yet visited. So I think I should draw that down. Or I should write this down. I visited 4. I visited 5. I visited 1. Oh, I can't write. That's sad. Okay. I visited 4. I visited 5. I visited 1. I visited 2. And I'm now at 0. What are the adjacent vertices to 0? That's 1 and there's 2. Did I already visit 1? I did. So I can't use 1. Did I visit 2? Yes, I did. So I can't visit 2 anymore. So that means my DFS stopped here. So I'm gonna go back to where I came from. I'm at 2. Is there any other adjacent vertices for 2 other than 0? There are none. Okay, wala na yung arrows pointing from 2 going to another vertex. So that means I'm done here. So I'll go back to its parent, 1. I went from 1 to 2 to 0. Is there still any other adjacent node? Yes, there is. There's 3. Have I visited 3? No, I have not. So I'm gonna visit 3. 3. 3 can point, or 3 can visit 0 and 2. But 0 and 2 have already been visited previously. So I'm done. I don't need to visit any more vertices. So I'll go back to 1. 1 has 1. Does 1 still have any adjacent vertices that haven't been visited? No, there isn't. So I'll go back to 5. Does 5 still have adjacent vertices that need to be visited? No. So I'll go back to 4. 4 visited 5, 1, 2, 0. And it's also visited 3 going from 1. So, are there still adjacent vertices I can visit? I can still visit 6. So I go to 6. 6 can visit 5 and 3. But 5 was already visited and 3 was already visited. So, I already stop. I go back to 4 and say there's no more vertices to visit. Everything is visited, so we are done. That's the mata-mata method. But if we were to draw this is how it would look like. I just realized this might be difficult. Is there a way for me to show this? Okay, let's just do this simulation. So I started at vertex 4. So let's just turn on my pen and we'll have an array called mark. For a moment, I want that to be darker. So I have an array called mark. Zoom 2, 3, 4, 5, 6, 7. Do I have 7 vertices? Yes, I do. 0, 2, 3, 4, 5, and 6. It told me to start with... Sorry, I wasn't actually even on my screen. So I have mark, and I'm going to start by saying everything is unvisited right now. These are all use. I shouldn't use U and V because I draw it very badly. Let's use 1 and 0, I guess. Okay, dili maklaro. So let's just say everything is unvisited for now. Okay? Everything is unvisited for now. And I'll start my DFS by calling DFS4. So DFS4 means I drew the number 4 here. That is my first vertex. And I'm going to set 4 to be visited. So 4 is now visited. What do I do next, guys? I'm going to check for my vertices. So I'm going to see my W1, W2. We have 5 and we have 6. Because we have 5 and we have 6. I'm going to check. Is 5 already visited? So I'm going to check. Is 5 already visited? No, it's not. So I am going to call DFS 5. So when I call DFS 5, that's basically the same as I'm drawing an arrow going down, going here, and I visited 5. So I'm going to update 5 to become visited. 5 is now visited. So I wish I could move this. I think we don't even need to do the WW thing. Let's just keep going. I'm currently now here. The only adjacent vertex I have is 1. So I am going to check. Is 1 already visited? No, it's not. So I'm going to draw another arrow, or I'm going to call DFS1 again. I'm going to call DFS again. So that's DFS 1. And I'm going to set 1 to visited. Okay? So I'm now here. I have 1, 2. I have 2 and 3 as my possible vertices to visit. And I'm going to visit most likely I'm always going to visit the smaller one. Because in this instruction, I said it's an ascending. So, let's visit 2. Let's check first 2. Is 2 already visited? No, it's not. So, I am going to draw 2. And I'm going to set 2 to become visited. So now I'm at 2. Who are adjacent to 2? I have 0 and basically just 0. So I am going to check. Is 0 already visited? No, it's not. So I am going to draw another tree arc going from 2 to 0. Good? And then I'm going to set this to 1 or visited. So I visited 0 as well. I'm now here. My adjacent vertices are 1 and 2. So I'm going to check for, first let's check with 1 because it's smaller. Is 1 already visited? Yes, it is. So that means I have a broken arc going from 0 to 1. Also, I just realized my drawing does not have arrowheads. There. So I've already visited 1. Let's see if I've already visited 2. Have I already visited 2? Yes, I have. So that means there's another broken arc going from 0 to 2. Is there any other node I can visit? No, there isn't. So I go back to 2. So I'm now here. Is there any other node I can visit from 2? No, there isn't. So I go back to 1. So now I'm at 1. Is there any other node I can visit? I've already visited 2. I haven't visited 3. So let's check. Have I already visited 3? No, I haven't. Therefore, I can draw another arrow going from 1 to 3. Good so far? And then, basically, I changed the value of 3 to be visited already. So now I'm here. I basically call DFS 3. The adjacent nodes or adjacent vertices for 3 are 0 and 2. 0 is already visited and 2 is already visited. So that means I need to draw an arc going from 3 to 2 and 3 to 0. And then I end my DFS. I go back to 1, check if I have any adjacent vertices. Wala na, si 2 and 3 only. So I go back to 5, check for adjacent vertices again. There isn't. So I go back to 4. Does 4 still have an unvisited adjacent vertex? Yes, he has 6. So I'm going to check. Is 6 already visited? No, it's not. Therefore, I'm going to draw an arrow going from 4 to 6. I'm going to set 6 to visited. And then I am going to check 6. 6 is adjacent to 5 and 3. But 5 and 3 are already visited. So that means I need to have some broken lines going from 6 to 5 and 5 to 3. Gets? I hope you guys were able to keep up. So after that, there's no more adjacent vertices to visit. I go back to 4. No more adjacent vertices to visit. I'm done. No more left to visit. So I'm going to check my mark. Are all the vertices already visited? Yes, they are. So I'm already done. I already have my spanning forest, which is this one. Amazing, guys. I hope you were able to keep up. So what's the answer of exercise 2? We'll just go here. So it's just similar to my amazing drawing, if I do say so myself. So that's how we came up with the answer. So for your activity, I'm sure you guys know how to do depth first search already by now. We can also do it using, if you want to practice even more and simulate even more, we can simulate it using this one. This amazing depth first search simulator provided by CSUSCFA, I don't know. Basta this website that I shared with you. So I'll show you how this works. We can just do the same thing all over again. So let's start with any vertex. Let's just say I'll start with vertex 7 and let's run DFS. Play. Okay, let's pause. So we started with vertex 7. So we set 7 to be true or it's visited already. Now for 7 can point, or 7 has a path going to 6 or an arc going to 5 or 6. And in this case, we are going for ascending order. So it's checking for 5. Is 5 already visited? No, it's not. So I'm going to set 5 to become visited. So it becomes true. Please don't mind the parent. We don't use this in our simulations. So let's just look at this. 5 became visited, so it becomes true. And now we're at 5. What do we do next? We are going to check for any adjacent vertex to 5. And the only one is 3. So I'm going to check, is 3 visited? Yes. No, it isn't. So I am going to set it to visited. And now I'm at 3. I'm going to do it all over again. I'm at 3. I'm going to check for any visited nodes or any adjacent nodes. The only adjacent vertex is 1. So I'm going to check, is 1 already visited? No, it isn't. So I am going to go to 1. I'm going to set that to visited. I'm now at 1. 1, look for adjacent vertices. 0 is not adjacent because 1 can't go to 0, but 2 can. So I'm going to go to 2. Is 2 visited? No, it's not. So I'll go to 2 and set it to visited. I'm now at 2. 2 is adjacent to 0 and 6. 2 is adjacent to 0 and 6. So we'll go for the smaller one, 0. Is 0 already visited? No, it's not. So I'm going to go to 0 and I'm going to set it to visited. I'm now at 0. I'm going to look for adjacent vertices, 1 and 3. 1 is smaller than 3, so I'm going to start by checking 1. Is 1 already visited? Yes, it is. So I don't need to do anything. So I'm going to check for 3. Is 3 already visited? Yes, it is. So I'm not going to do anything. So that means I have no more vertices to check. I will now go back, or my DFS ends, and I'll go back to my parent, which is 2. From 2, I'm going to check, do I still have adjacent vertices that haven't been checked? 6. I have 6. So I am going to check. Is 6 already visited? No, it's not. So I'm going to 6. And I'm going to set 6 to visited. I'm now at 6. 6 can go to 5 and 4. I'm gonna check first the smaller value, 4. So is 4 already visited? No, it isn't. So I'll go to 4. I'm now at 4. And I'm going to check again for adjacent vertices. 4 is only adjacent to 2. So 4 checks with 2, DFS 2. Is 2 already visited? Yes, it is. So I don't need to visit anymore. Does 4 still have any adjacent vertex to visit? Yes, I have 7. So I'm going to check 7. Is 7 already visited? That's true. So I don't do anything. So I'll go back to my parent, 6. 6 still has something that wasn't checked, which is 5. So I'm going to check. 6 to 5. Is 5 already visited? Yes, it is. So I'm not gonna do anything. I'm gonna go back to my parent, which is 2. My DFS call for 6 ended. Now I'm at 2. Does 2 still have any arrow or arc going from 2 to another vertex? Wala na. So my DFS 2 ends and I go back to my parent 1. Does 1 still have any arcs left unchecked? No, there isn't. So I go back to my 3 or my parent 3 and DFS 1 ends. Does 3 still have any adjacent vertices to check? Wala na. So I'm gonna go back. My DFS 3 ends and I go back to 5. Does 5 still have any adjacent thing to check? Wala na. So I go back to 7. And now I am at... Oh, I did actually have something to check. Sorry. 5. 5 check 3 and 5 can actually have an arc going to 7. So we need to check. 5 to 7. Is 7 already visited? It is. So do nothing. So meaning my DFS for 5 ends and I'm back at 7. Does 7 still have anything to check? There is, which is 6. Is 6 already visited? Yes, it is. So it's done. Go back to 7. Is there still anything else that I need to check? Wala na. So that's the end of my DFS. I was able to visit all of the different nodes. Amazing. So this lecture has been going on for quite some time. We have a quick activity provided here. So in this exercise that I drew for you, I assumed that we were always going to visit the 5th or the smaller index or smaller vertex. Can we do that again? But this time, the adjacent vertices are arranged in descending order. Meaning, if I start from 4, rather than going to 5, I'll go to 6 first. 6 can point to 5 or 3 or has an arc from 5 to 3. So I go to the higher value because it's descending. So I'll go to 5. And so on and so forth. Can you try to simulate this and show me or show your classmates what you've done? At the end of the day, we were able to get our DFS. Apparently, we are not yet done with this lecture. So let's keep going. What is a depth first number? So yun ra kaini si depth first number. It is an array containing, rather than containing visited or unvisited, it contains the number assigned to the vertex according to the when the vertex was first marked. So in this case, vertex 0, I started at vertex 0. So I visited vertex 0 first. After visiting vertex 0, I visited vertex 1. So vertex 1 was visited second. After vertex 1 was visited, what did I visit next? I visited vertex 2. So vertex 2 was visited the third. From 2, I hope we had that here. From 2, I could visit index 0, but it's already been visited. So I ended my DFS and I started to visit 3. So index 3 or vertex 3, was the fourth one to be visited. So what does that mean? It just means it's the order assigned to the vertex according to the order in which the vertex was first marked. So for example, in this specific exercise, let's say I visited 4 first. That means in my DF number, 4 should be 1. In my drawing here, kanina, I visited 4 first, then I visited 5 next. So in my DF number, this should be 1, this should be 2. Very simple. So apart from this specific exercise that you guys should be doing, wherein you try to do DFS in descending order, try to do this one too and give me the def first number. Okay? I hope you guys were able to get this lesson. Napaday gamay. Sorry. These are some of the observations. For observation 1, W is a descendant of V if and only if the DF number for V is greater than or equal to DF number of W, which is greater than or equal to the DF number of V plus number of descendants of V. Kani siya nga statement, just trust that it is always true. Kani ang mo make more sense. Forward arcs go from lower numbered to higher numbered vertex. What does that mean? It's not about 0 going to forward arcs 0 going to 2 because it's 0 going to 2. It's actually based on your DF number. DF number of 0 is 1. DF number of 2 is 3. 1 is lower than 3, so there is a forward arc from 0 to 2. Back arcs go from a higher numbered to a lower numbered vertex. What does that mean? There's a back arc from 2 to 0. That just means 3 and 1. What's bigger? 3 is bigger than 1, so there's a back arc from 2 to 0. There's a cross arc from 5 to 1. If we check index 5, 5 has a DF number of 6. And there is a cross arc from 5 to 1 and 6 to 2. So it's considered a back arc. More na siya, guys. I hope you understood DFS. This is the longest lecture ever. So I hope you guys practice with these specific activities. Okay, this would be very helpful for you guys. And if you want to try to practice, you can also practice from here. You can generate a new graph and you can try to simulate from here as well. Okay, we're good. See you in the next lecture. We will be talking about BFS. Bye.